It was already there first. That is the claim racing across the internet after Webb looked into the early universe. But did a black hole really show up before its own galaxy, or are we forcing a wild headline onto a harder truth? The real question is simple. What exactly did Webb see, and does it prove the black hole came first? At first glance, the story sounds impossible. A galaxy is supposed to build the stage, and the black hole is supposed to grow in the middle much later. Subscribe now if you want the full picture before the easy version takes over. Stay with this channel, and you stay inside the story while the facts are still being sorted. To understand why this claim hits so hard, we have to go back to the old idea that most astronomers trusted for years. First came stars. Then came galaxies that slowly got bigger. Then, in the deep center, black holes fed on gas and grew with the galaxy around them. That picture was neat, clean, and comfortable. It also seemed to match what we saw in the nearby universe. In large galaxies today, the mass of the central black hole and the mass of the stars in the galaxy usually track each other. In plain words, bigger galaxy, bigger black hole. Not perfect, but close enough that many researchers saw it as a rule of growth. Then James Webb started looking where older telescopes could barely see. Webb works in infrared light, which helps it catch stretched, ancient light from the early universe. That matters because the farther out Webb looks, the farther back in time it sees. When it looks deep enough, it is looking at space as it was only a few 100 million years after the Big Bang. That is where the first crack appeared. Webb did not just find a few early galaxies. It found a surprising number of bright, compact, and strange ones. Some looked too mature. Some looked too red. Some looked like they were hiding something in their centers. Instead of cleaning up the story, Webb made the early universe look messy. One name began to matter very fast: UHZ-1. This object was seen as it was about 470 million years after the Big Bang. That means the light left it more than 13 billion years ago, when the universe was only about 3% of its current age. In normal human terms, this was cosmic babyhood. UHZ-1 did not stand out because it looked pretty. It stood out because Webb and NASA's Chandra X-ray Observatory together caught signs of a feeding black hole inside it. Webb found the distant galaxy in infrared light. Chandra picked up X-rays, the kind of high-energy signal black holes often create when gas falls inward and heats up to extreme levels. Now comes the detail that changed everything. The black hole tied to UHZ-1 was estimated at about 10 million to 100 million times the mass of our Sun. Researchers then compared that to the mass in the galaxy's stars. What they got was shocking. The black hole may make up a huge fraction of the galaxy's total stellar mass, at minimum about 2/3. That is not how the nearby universe behaves. In many large galaxies around us, the central black hole is more like a tiny fraction of the stellar mass, often closer to 1,000th. UHZ-1 was nowhere near that pattern. If the estimate was right, the black hole was not just big, it was absurdly big for the little system around it. And that is where the headline was born. If the black hole is that overgrown, then one simple thought follows. Maybe the black hole started first. Maybe the stars in the host galaxy had barely begun building when the black hole was already massive. Maybe what Webb found was not a normal galaxy with a black hole inside it, but a black hole racing ahead of the galaxy itself. That idea did not come from excitement alone. It came from a timing problem. Under the standard path, black holes start from the remains of giant stars. Those seed black holes are much smaller, often around tens or maybe hundreds of solar masses. To grow from that to tens of millions so early, they would need time the universe may not have had. So researchers started testing harder options. One option was extreme feeding. If a black hole gulps gas as fast as physics normally allows, and keeps doing that without many breaks, it can grow much faster. Another option was an entirely different birth. Instead of starting from a dead star, maybe some black holes were born large, from giant clouds of gas collapsing almost directly. This is the point where the story gets dangerous, because one dramatic sentence can hide two very different meanings. Saying a black hole is older than its galaxy could mean it literally formed before the galaxy existed at all. Or it could mean the black hole began growing before most of the galaxy's stars formed, which is a smaller but still huge claim. Those are not the same thing. Before we go further, make your call now. Did Webb catch a black hole that truly came first? Or are we looking at a black hole that simply grew much faster than its galaxy? Drop your guess in the comments before the next piece lands. The next piece came from the way UHZ-1 was found. It sits behind a massive galaxy cluster called Abell 2744, and that cluster acts like a cosmic magnifying glass. This effect is called gravitational lensing. In simple terms, the gravity of the foreground cluster bends light and makes the far object behind it easier to see. Without that help, UHZ1 might have stayed hidden. That extra brightness is useful, but it also means the measurements are delicate. If the lensing amount is off, then the mass estimates can shift. Researchers know this, and they factor it in. Even so, the basic result held enough force to make scientists say the black hole could have formed before the bulk of the stars in its host system. Notice the wording there, not before all matter in the region, not before any structure existed, before the bulk of the stars. That sounds less explosive than the headline, but it is still a direct challenge to the old picture. The old picture says stars build up, galaxies deepen, and black holes rise with them. UHZ1 hints that the order may sometimes flip. Then another object added pressure from a different angle. Its name was GNZ11. Astronomers had known GNZ11 before Webb, but Webb gave them a much deeper look. They found signs of an active black hole there too, and GNZ11 is seen just 400 million years after the Big Bang. That made it, at the time, the oldest black hole ever observed. The black hole in GNZ11 was not as huge as some later monsters, but it was still a few million times the mass of the Sun. That alone was a problem. If it started from a small dead star seed and grew at the expected rate, there should not have been enough time. Researchers said two main answers were left standing. Either it was born big, or it fed far faster than expected. GNZ11 also added another twist. The black hole may have been blasting material outward in strong winds while also feeding hard. That matters because gas is the fuel for new stars. If the black hole is throwing that gas away, it can slow star birth in the host galaxy. In plain English, the black hole may not just be growing inside the galaxy. It may be choking the galaxy that is trying to grow around it. That turns the story upside down. We are taught to think of galaxies as homes and black holes as the strange things living in their centers. But in some early systems, the black hole may act more like the loudest force in the room, pulling in gas, heating it, and blasting part of it back out. Instead of the galaxy shaping the black hole may be shaping the galaxy from the start. Now hold that thought, because another Webb result widened the puzzle instead of closing it. In 2023, the Sears survey found an active black hole in a galaxy called Sears 1019, seen about 570 million years after the Big Bang. Its black hole mass was around 9 million suns, smaller than the giant monsters found by older telescopes, but still surprisingly mature for such an early time. CEER's 1019 mattered for a special reason. It showed that the early universe was not only hiding extreme billion solar mass giants. Webb could also detect lighter black holes that older tools missed. That suggested the early universe may have been full of active black holes across a wide range of sizes. Once that idea entered the picture, the mystery grew larger, not smaller. Because if there were many young black holes already active that early, then UHZ1 might not be a freak accident. It might be one visible example of a broader hidden population. That would mean the old timeline was not just bent in one place. It might need rewriting across the whole first billion years of cosmic history. Here is where things sharpen. If UHZ1 was only one strange outlier, the old model could survive with a patch. But if Webb keeps finding early galaxies with overgrown black holes, then the order of growth we trusted for decades may be wrong at the deepest level. Pause here and put your prediction on record. When Webb kept looking, do you think it found calmer, more ordinary systems, or even more objects pointing to black holes growing too soon? Leave your pick before we move on. The answer was worse for the old model. Webb began finding a class of objects nicknamed little red dots. These are small, distant, very red sources in the early universe. At first, nobody was fully sure what they were. Some looked like compact galaxies. Some seemed to hide dense gas and dust. Some gave off signals that made astronomers suspect feeding black holes. In 2025, one of these objects, called Canucks LRDZ 8.6, pushed the problem further. Webb data showed signs of an accreting supermassive black hole inside it only about 570 million years after the Big Bang. Researchers compared the black hole mass with the mass in the system's stars and found the black hole was overmassive for its host. Again, the black hole seemed to be ahead of the galaxy, not growing politely beside it. That was not proof that every little red dot hides a giant black hole, but it showed the idea had teeth. If many of these tiny red objects contain black holes growing at extreme speed, then Webb may be seeing an early stage of how some of the universe's first quasars were built. Quasars are the blinding beacons powered by black holes feeding at huge rates. They are among the brightest things in space. And that matters because quasars are another timing headache. Even before Webb, astronomers knew of gigantic black holes less than 1 billion years after the Big Bang, some over 1 billion solar masses. Those were already hard to explain. The usual escape route was that we were only seeing the brightest, rarest monsters. But Webb began filling in the middle ground. That makes the escape route narrower. So what are the main explanations now? There are 3 serious paths. First, black holes may have started from unusually heavy seeds. Second, they may have fed at or above the expected limit for long stretches. Third, we may be seeing a mix of both, where some start larger and then also eat very fast. None of those answers is fully settled. The heavy seed idea is easy to say and hard to prove. In this picture, a huge cloud of gas in the early universe avoids breaking up into stars and instead collapses almost directly into a black hole. That could create a seed with 10,000 or even 100,000 solar masses right away. If that happened, the later growth problem becomes less severe. But there is a catch. Gas clouds do not usually behave that cleanly. They cool, they fragment, and they often make stars. To get direct collapse, conditions may need to be just right. The gas may need to stay hot. The area may need strong radiation from nearby sources. The cloud may need to avoid spinning itself apart. This is possible, but it is not easy. The fast-feeding idea has its own catch. Black holes cannot simply eat forever with no pushback. As gas falls in and heats up, it shines. That light and energy can push on the inflowing gas. At some point, the pressure fights the fall. This creates a rough ceiling on how fast a black hole should steadily grow. Breaking that ceiling for long periods is hard. Still, hard is not impossible. The early universe was richer in cold gas than the modern one. Galaxies were smaller, closer together, and more chaotic. Mergers may have driven gas straight into central regions. Dense streams of matter may have fed black holes from the cosmic web itself. In short, early space may have offered a much wilder menu than we first imagined. Now we reach the part that changes the tone of the whole story. This is no longer just about one object and one headline. It is about whether our map of the first cosmic dawn is missing a major engine. If black holes grew early and hard, then they may have helped control how the first galaxies lit up, how fast stars formed, and how matter organized itself in the young universe. That is a much bigger claim than most headlines admit. The question is not only, did one black hole beat its galaxy to the punch? The question is whether black holes were active builders, blockers, and sculptors from the opening chapter onward. If that is true, then the early universe was not star first and black hole later. It was a tug of war from the very start. Right before the next turn, I want your best theory. Was the real driver giant birth seeds, non-stop feeding, or some mix of both? Put your answer in the comments now because the next clue changes what each option means. The next clue is this. We still do not directly see a black hole being born. We infer it from the light around it, the gas it excites, the X-rays it sends out, and the effect it has on its host. That means every strong claim carries uncertainty. Distances can shift, masses can shift, models can improve. Good science moves by reducing those gaps, not by pretending they do not exist. So, does that uncertainty rescue the old picture? Not really. Even if some masses are revised down, the pattern keeps returning. Webb continues to find black holes that appear surprisingly mature for their time. And when several separate objects point the same way, the burden changes. Now the old model has to explain why so many early systems look older than expected. There is another reason the older than its own galaxy phrase spread so fast. It captures a real intuition. Galaxies feel like the large thing. Black holes feel like the small thing in the middle. So when the black hole seems too massive for the galaxy, our minds turn that into a story about order. The child has become larger than the house, so maybe the child was there first. That metaphor is useful, but only up to a point. A galaxy is not a finished object that appears in one moment. It is a process. Stars form over time. Gas falls in over time. Mergers reshape everything. So when researchers say the black hole may have formed before the stars in its host galaxy, they are talking about which part of that process got a head start, not about a black hole floating alone forever and then ordering a galaxy around it. Even so, the core shock remains. In UHZ1, the black hole may hold a stunning share of the mass compared with the stars. In GNZ11, the black hole appears far too mature far too early. In CEERS 1019 and other early systems, smaller active black holes show this was not only a story about the brightest giant quasars. In little red dots, the pattern may be showing up again. Something important follows from that list. These objects are not all identical. Some are X-ray bright, some show broad spectral lines in Webb data, some are dusty, some are compact, some may be shaped by mergers. That variety matters because it hints we may not be looking at one single path to early black hole growth. Nature may be using several routes at once. That is uncomfortable because humans like one clean answer. We want the one mechanism, the one birth channel, the one neat fix. But the universe often refuses that kind of simplicity. Some black holes may start big, some may feed above the usual limit for a while, some may sit in unusually rich gas flows, some may grow through repeated collisions and mergers. Reality may be a crowded mix. And if that is true, then the real discovery is even deeper than the headline. Webb may not have caught a cosmic exception. It may have exposed how narrow our older view really was. We imagined the first few 100 million years as a slow build. Webb keeps showing flashes of speed, imbalance, and competition. That mismatch is part of what makes Canucks LRDZ 8.6 so interesting. Researchers described it as compact and still early in its development, yet its central black hole seemed too large for the amount of starlight around it. When the center looks older than the city around it, the old rule starts to wobble. You are no longer watching smooth, shared growth. You are watching a race where one runner may have left far too early. There is another layer to this. Black holes do not glow by themselves. The light comes from matter falling toward them. That means a dim black hole can be hard to spot even if it is there. So every time Webb finds one of these early active black holes, astronomers also have to ask how many others are hiding because they are quieter, dustier, or pointed away from us. The visible sample may be only the tip of a much larger buried population. If that hidden population is real, the consequences spread everywhere. Reionization, the era when early light changed the state of gas across the universe, may have been shaped not only by stars but also by black holes. The heating of gas inside young galaxies may have been stronger than many models assumed. Even the way the first galaxies stopped or slowed their own star formation may need new inputs if central black holes were already punching above their weight. This is why scientists are being careful with language even while sounding excited. They know a flashy phrase travels faster than a measured one. Saying a black hole may predate the main stellar buildup of its host is precise but less dramatic. Saying the black hole is older than its own galaxy is sharper and easier to spread. The truth lives between those two styles, and it is our job to stay with the harder version. Even the mass ranges show why caution matters. In UHZ1, the black hole estimate spans a broad interval, from around 10 million to 100 million solar masses. That is a big range. But here is the key point. Even the lower end is hard to fit comfortably into the old timeline if you start from small seeds and ordinary growth. The upper end is the version that really snaps the model in half, but the lower end still bends it badly. Researchers are also watching for false alarms. Strong star formation can sometimes mimic part of a black hole signal. Dust can hide the true shape of a source. Lensing models can change brightness estimates. A merger can make one object look like several clumps, or several clumps look like one system. Good teams know all of this, which is exactly why the continued pattern across different objects feels so important. That is the heart of the investigation. Any one object can fool you. A pattern that repeats across methods, dates, and teams is much harder to wave away. UHZ1 raised the alarm. GNZ11 made the timing problem louder. CEERS 1019 showed lighter active black holes were already present. The little red dots suggested this may be part of a larger family. Each piece alone is interesting. Together, they lean in the same direction. There is a simple growth math problem buried under all of this drama. Start with a seed black hole around 100 solar masses, the sort you might get from a dead giant star. Let it grow steadily under the usual limit. To reach millions or billions of solar masses, you need many doubling steps, and each step takes time. When the universe is only 400 to 570 million years old, there may not be enough time left on the clock. That is why the phrase "born big" keeps returning. If the seed starts at 10,000 or 100,000 solar masses instead, you remove a huge number of doubling steps at the start. The growth path becomes much less desperate. You still need fast feeding, but not a miracle every moment. This is one reason the direct collapse idea has stayed alive, even though proving it in nature is so difficult. But there may be an even stranger option. Some theorists think dense star clusters in the early universe could create runaway chains of collisions that leave behind a larger black hole seed than a single dead star would. That would sit between the tiny seed and the direct collapse seed ideas. It would mean nature had more than two doors open, not just small seeds or huge seeds, but an in-between path as well. Then there is feedback, a word that sounds technical but means something familiar. A growing black hole changes the environment that is feeding it. It can heat the gas, it can blow winds, it can push matter away. So the black hole and the galaxy are in a fight and a partnership at the same time. One feeds the other, then harms the source, then changes the next round of growth. That feedback loop may explain why the story feels unfinished rather than solved. If a black hole briefly gets ahead, it might then choke the very gas that helped it surge. If a merger drives in fresh fuel, the surge might return. The balance can swing. So when we see a system at one moment in deep time, we may be catching one frame of a violent process, not the whole movie. This is also why future observations matter so much. Webb can revisit these targets with longer exposure times and better spectra. ALMA, the giant radio telescope array in Chile, can help trace cold gas and dust that Webb alone cannot map as easily. X-ray telescopes can test how active the center really is. Each extra look removes one layer of guessing and turns a bold story into a sharper one. And remember something else easy to miss. We are not seeing these galaxies as they are now. We are seeing them as they were when their light began its trip toward us more than 13 billion years ago. Whatever happened to UHZ-1 or GNZ-11 afterward is long over. The drama is ancient. But because light takes time to travel, the ancient drama is reaching our eyes only now. That fact alone gives this topic its strange power. We are trying to reconstruct a scene that played out before Earth existed in its current form, using faint, stretched light and careful models. And still, from that tiny signal, we can ask whether a black hole got the jump on a galaxy. It sounds impossible, yet step by step, the measurements are turning that impossible question into a serious one. We are close to the verdict now. Before I give it, say what you think the safest answer is. Yes, Webb basically found a black hole older than its galaxy, or no, that headline pushes the facts too far. Leave your final call before we settle it. Here is the verdict. If you read the headline in the strictest possible way, it goes too far. Webb has not proved that a black hole popped into existence long before any galaxy around it existed in the fully separate, dramatic way people imagine. What Webb has shown is almost as unsettling. In some of the earliest known systems, the black hole appears to have started growing before most of the host galaxy's stars were in place, or it grew so fast that the galaxy could not keep up. That is not a small correction. That is a major shift in order. It means the old story of galaxies patiently assembling first and black holes following along later is no longer safe as a universal rule. In at least some early systems, the black hole may have been one of the first dominant structures, shaping the galaxy while the galaxy was still becoming itself. So the bold opening claim was both wrong and right. Wrong if you take it as a literal simple fact with no uncertainty. Right if you take it as a rough description of the deeper problem Webb has uncovered. The black hole in objects like UHZ-1 seems too far ahead, too early, and too powerful for the old timeline. That is why the claim refuses to die. And that is why this matters to all of us, even if you never think about galaxies on an average day. We are trying to answer one of the oldest human questions there is. How did structure appear out of the early chaos? How did the universe go from hot, dark simplicity to stars, galaxies, planets, and eventually people who can ask where they came from? Black holes were once treated like the final act, the graveyards left behind after stars lived and died. Webb is forcing a very different possibility into the open. In some places, black holes may have been early organizers, early destroyers, and early architects all at once. They may have helped decide which galaxies bloomed, which stayed small, and which paths cosmic history followed. That changes how we think about the sky above us. It means the universe may have built some of its biggest engines before it built the full cities around them. It means the centers of galaxies were not always quiet passengers waiting for time to pass. Sometimes they may have been aggressive, hungry, and in control from almost the very beginning. And there is one more reason to care. This story is not finished. More Webb observations are coming. More early galaxies will be tested. Better spectra will narrow the masses. New X-ray missions may add stronger confirmation. The verdict we gave tonight is strong, but it is still alive, and living questions are the ones that change science the most. If you want to stay ahead of stories like this, subscribe and turn on notifications now. Then tell me in the comments which idea you trust most. Black holes were born big, they fed too fast, or the early universe was running on several wild paths at once. Share this with one person who loves space mysteries and will argue about the ending. Thanks for being here.